Okay, in this video we are going to look at sub-matrices of the incident graph, and we will prove a property of the sub-matrices of the incident graph. So let's start by looking at the sub-matrices of the incident matrix. Okay, so let H be a subgraph of a graph G, and let A of H and A of G be the incident matrices of H and G respectively. For example, okay, let's consider this graph G, and we can very easily see that this is the incident matrix for this graph, and this is going to be our H. Okay, and let it be a subgraph of G. Okay, so let's consider a subgraph of this graph. Okay, so that contains these four vertices. Okay, and maybe something like this. So it contains all the vertices here: V1, V2, V3, V4, and suppose that our subgraph has these edges. Okay, so it has E1, E2, E3. Okay, and let this be our graph H, and very easily we can see that okay, this H is a subgraph of G, and so okay, let's find the incident matrix for this graph. So it has four vertices, so it will have four rows, E3, V4, and the number of edges is 3, E1, E2, E3. So that says it has three columns, E1, E2, E3. Okay, and here this E1, it is incident on V1 and V2, so we have two ones here and the remaining 0. E2 is incident with V1 and V3. Okay, so we have a 1 here, 0 here, 1 here, 0 here, and E3 is incident with V3 and V4. Okay, so we have V3 and V4, so we have two ones here and remaining 0. So this is going to be our incident matrix for this subgraph H. Okay, so we can very clearly see that this matrix A of H is a submatrix of AG, possibly with rows and columns permuted. That is okay, but most important thing is that we can see that this A of H is a submatrix of A of G. Okay, so let's see whether that is true here. Okay, so if you look this graph, okay, this matrix, we can see that it occurs as a submatrix of this matrix, right? So in this case, that submatrix happen to be this particular thing. Okay, so that is going to be true for any subgraph of this graph and the incident matrix of that graph. Okay, so we will see that the incident matrix of any subgraph will be a submatrix of this graph, possibly okay, rows and columns permuted. Okay, and that's what I said here, possibly with rows and columns permuted. And here the most important thing is that okay, if you look at these submatrices, we can see that there is a one-to-one correspondence between each n by k. So we need to consider every row, but only a subset of edges. Okay, that's what this thing says, n by k, submatrix of AG, and a subgraph of G with k edges. Okay, where k is strictly less than m, and n is the number of edges. Okay, so there will be one-to-one correspondence between this submatrix and a subgraph with k edges. Okay, for example, if you look at this particular graph, okay, we can see that. So suppose that we are going to consider only say okay E1 and E3. Okay, if we consider E1 and E3, the subgraph will look something like okay, this. So this is V1, V2, V3, V4, and let's consider only these two edges. So E1 connects V1 and V2, and E3 connects V3, V4. Okay, so we will have this subgraph. Okay, and that subgraph, it will be it will correspond to only this particular submatrix. Okay, so that submatrix will be like, okay, this first column and the third column 0 0 1 1. So this is going to be a one-to-one correspondence. So if you give me this matrix, then I could find, okay, this unique submatrix or subgraph of this graph. And similarly, if you give a subgraph of this graph with n vertices, okay, then there will be a unique submatrix of this graph, which looks something like this. Okay, and let's look one more example. Okay, again we are looking at some n by k, where this k is strictly less than m. In this case, n is equal to 4 and m is equal to 1 2 3 4 5. Okay, so let's look at, say, a 4 by 3 matrix and see what is going to happen. So let's pick these three columns. Okay, so we are considering this subgraph v1 v2 v3 v4, and this e3, it connects v3 and v4, so that is our e3. Okay, then e4, it connects v2 v3. Okay, v2 v3, this edge e4, and e5, it connects v2 v3, so that is our e5. Okay, so if you consider this particular submatrix, and that corresponds to this subgraph of this graph. Okay, and similarly, if you consider this subgraph, that corresponds to this submatrix, and this is going to be a one-to-one correspondence. Okay, and that's what I said here. Okay, so very easily we can see that there is a one-to-one correspondence between each n by k submatrix of the incident matrix of G, okay, and a subgraph of G with k edges, where k is strictly less than m and n is the number of vertices in the graph. Okay, so this is how a submatrix of an incident matrix looks. Okay, so we saw from these examples that this kind of one-to-one correspondence holds. Okay, and let's go and prove a property of the submatrices of the incident matrix. Okay, so this is not capital A. So the statement reads as follows: let A of G be the incident matrix of a connected graph G with n vertices. Okay, so we consider any n minus 1 by n minus 1 submatrices. Okay, submatrix of A of G. Okay, and that matrix is non-singular if and only if. Okay, it is non-singular if and only if. Okay, here what we are doing is we are choosing some edges here, right? If and only if the n minus edges that we chose here corresponds to, it corresponding to the n minus columns of this matrix constitute a spanning tree in G. Okay, so let me read this particular statement once more. Okay, let A of G be the incident matrix of a connected graph G with n vertices. Okay, and n minus 1 by n minus 1 submatrix of A of G is non-singular if and only if the n minus 1 edges corresponding to the n minus columns of this matrix, AG matrix, constitute a spanning tree in G. So before proving this theorem, let's look at some examples. Okay, I think the statement is clear. So what we are doing is we are considering an n by 1 by n minus 1 submatrix of the incident matrix of the graph, and if this matrix is singular, okay, or this matrix is singular if and only if, okay, those n minus 1 edges corresponding to the columns that we chose here constitute a spanning tree in G. Okay, so let's consider okay, this graph G and the incident matrix of this graph. Okay, A of G. Okay, so that says we need to consider n minus 1 by n minus 1, right? So okay, so let's go from a spanning tree to a matrix. Okay, so let's consider a spanning tree in this graph. Okay, so that spanning, it contains all the vertices by definition, and in this case 3 edges. So let's consider this spanning tree: E1, E2, E3. Okay, so here we are considering this submatrix. Okay, so this is V2, V1, V3, V4. Okay, so let's consider E1, E2, E3. So we are considering this portion of this graph. Okay, and moreover we need to delete one row here, right? So we need to consider n minus 1 by n minus 1 submatrix. Okay, so let's delete this particular thing. Okay, so here we can see that if you look at this particular graph, okay, so this not particular graph, okay, this submatrix, so that is going to be in this case a 3 by 3 matrix. Okay, and if you find the rank of this matrix, we will see that the rank of this matrix will be equal to 3. Okay, so we started with a spanning tree and this n minus 1 by n minus 1 submatrix. Okay, and we see that in this case this matrix 1 1 0, the 1 0 0 0 1 1. Okay, this is a full rank matrix. It is not possible to write any of these rows as a linear combination of other. Okay, or you can do Gaussian elimination and you can verify that the rank of this matrix, okay, is equal to 3. So it has full rank. Okay, so that says this statement holds for this spanning tree. So if we start with the spanning tree and if you consider a submatrix corresponding to that spanning tree of order n minus 1 by n minus 1, okay, then that matrix will be a non-singular matrix. Okay, and that's what we are saying here. And n minus 1 by n minus 1 submatrix of A of G is non-singular or invertible if and only if the n minus 1 edges corresponding to the n minus 1 columns of this matrix constitute a spanning tree in G. Okay, so let's look at one more example where this chosen subgraph or chosen spanning tree, okay, chosen subgraph is not a spanning tree. Okay, and if that is the case, then this matrix must be singular. Okay, it must be non-invertible. Okay, so let's go and see what is going to happen. Okay, so for that purpose, okay, so let's consider okay, this subgraph V1, V2, V3, okay, and V4. Okay, let's consider this cycle. So there is a cycle, so that is not a tree anyway. Okay, so let's consider this one. Okay, so it is not a spanning tree. Okay, so anyway, let's delete this row, and here we have these 3 edges E1, E2, E5. Okay, so we are deleting this row completely and we are considering this submatrix. Okay, 3 by 3 submatrix 1 1 0. Okay, E1, E2, 1 0 1 and E5. Okay, 0 1 1. So here we are considering these 3 columns E1, E2 and E5. So we have 1 1 0, 1 0 1, 1 1 1. Okay, so we have this matrix. Okay, so here very easily we can see that okay, this matrix, it has no full rank, it is a singular one. So if we add these 3 rows and taking modulo 2, so 1 plus 1 is 2, 2 modulo 2 is 0, so 1 plus 1 is 2, okay, modulo 2 is 0, 1 plus 1, okay, is 2 modulo 0, so we will get 0. So that says these 3 rows are dependent. So this matrix is a singular or non-invertible matrix. Okay, so that says if you consider a submatrix, okay, in this case n minus 1 by n minus 1, okay, for this example 3 by 3 submatrix that is not invertible, okay, then the subgraph, okay, here it won't corresponds to a spanning tree kind of thing, okay. So that's what this statement says. So and n minus 1 by n minus 1 submatrix of the incident matrix of G is non-singular if and only if the n minus 1 edges corresponding to the n minus 1 columns of this matrix constitute a spanning tree. So that's what we saw from this example and this example, okay, and let's go and prove this statement. Okay, so let G be a connected graph with n vertices and m edges. N vertices and m edges. Okay, since G is connected, we can see that the number of edges is greater than or equal to n minus 1. Okay, well, since a tree is a minimally connected graph, okay, a tree with n vertices has n minus 1 edges, okay, and so that says since, okay, this G it could be more than a tree, so that says the number of edges must be greater than or equal to n minus 1, and since this is connected, okay, since G is connected, m is greater than or equal to n minus 1. Okay, so let's look at the incident matrix of this graph G and see what is going to happen. Okay, so let A of G be the incident, okay, incidence matrix of G, okay, so that A of G it has n rows, okay, where this n corresponds to the number of vertices, okay, n rows and m columns, and these columns corresponds to the number of edges. Okay, and again we can see that m is greater than or equal to n minus 1 since the graph is connected, okay. And from the previous discussion of submatrices, okay, we know that every square submatrix of order n minus 1 by n minus 1 in the incident matrix is the reduced incident matrix of some subgraph H in G with n minus 1 edges and vice versa, okay. So that's so when we discuss, okay, this thing, so from that discussion we know that every square submatrix of order n minus 1 by n minus 1 in the incident matrix of the graph G, okay, is the, so there is a one-to-one correspondence, okay, that's why is the reduced incident matrix of some subgraph some subgraph H in G with n minus 1 edges and vice versa. Okay, so we are using this particular thing here, that's it. So we saw that there is a one-to-one correspondence between each n by k submatrix of AG and a submatrix of G with k less than m edges. Okay. So that says every square submatrix of order n minus 1 by n minus 1 in the incident matrix of G is the reduced incident matrix of some subgraph H in G with n minus 1 edges and vice versa. Okay, so here we have this square matrix. So this is a square matrix anyway. So we know that a square submatrix of the incident matrix is non-singular, okay, if and only if the corresponding subgraph is a tree. Okay, so we proved in the previous video that result. Okay, so from the previous video we know that a square submatrix. So anyway, okay, this particular thing it is a square matrix, right? Every square submatrix of order n minus 1 by n minus 1 in AG is the reduced incident matrix of some subgraph H in G with n minus 1 edges and vice versa. Okay, and from the previous video we know that a square submatrix of A of G is non-singular if and only if the corresponding subgraph, okay, corresponding subgraphs, okay, so SQUARE, okay, square submatrix of A of G is non-singular if and only if the corresponding subgraph is a tree. Okay, we proved that statement in the previous video. Only if the corresponding subgraph is a tree. Okay, so clearly the tree is a spanning tree because it contains n minus 1 edges of the n vertex graph. Okay, so clearly this particular thing, it's a tree, subgraph is a tree, and that is a subgraph, okay, and it contains all the vertices also. Okay, so clearly the tree is a spanning tree because it contains n minus 1 edges of the n vertex graph. Okay, so that says this particular thing, this n minus 1 by n minus 1 submatrix of AG is non-singular if and only if n minus 1 edge corresponds to the n minus 1 columns of this matrix form a spanning tree. Okay, so clearly the tree is a spanning tree because it contains this n minus 1 edges. Okay, since we have these n minus 1 edges and we have a graph with n vertices, right? Okay, so hence n minus 1 by n minus 1 submatrix of the incident matrix of G is non-singular, okay, non-singular or invertible if and only if edges corresponding to those n minus 1 columns of a G. Okay. So if edges corresponding to n minus 1 columns of this matrix form a spanning tree. Okay, and that's what we want to prove anyway. So that, and hence the proof. Okay, so in this video we look at the submatrices of the incident matrix, and we proved a property. Okay, this property, a property of a submatrix of the incident matrix. Okay, so we prove that if, okay, let A of G be the incident matrix of a connected graph G with n vertices. Okay, then we have this result, and n minus 1 by n minus 1 submatrix of the incident matrix of graph G is non-singular if and only if, okay, the n minus 1 edges corresponding to the n minus 1 columns of this matrix, the incident matrix of G, AG, constitutes a spanning tree in G.